Hey guys, this is really going to be all of chapter 22. Shoot, that should say 22, Mr. Welch. Let's get back over here. Jeez. Everybody makes mistakes sometimes. I just only make them when I'm being recorded. Okay, so chapter 22 video, this is just going to be one thing for everything. And we're only talking about a couple of basic ideas. So we have, we talked about electricity, we've talked about magnetism and how they're interconnected. And it seems like whenever we run a current, that there's this magnetic field that's induced, and then whenever we alter a magnetic field, there seems to be some sort of variation in current or some sort of voltage that's induced. And it turns out that there is a direct relationship between magnetic fields and electric fields. And if we run what's called an electromagnetic wave, okay, if we look at like light or radio waves or microwaves, radiation, all forms of radiation that travel as waves, that they follow, if we look at the magnetic field, as it varies, the electric field will vary as well. This is a little bit hard to draw, but try to do the best you can to stay with me. If you could imagine my electric field, okay, electric field is in purple here. And, let's get a black line out here. And there's a center line that runs through all that, right? Okay. So imagine that this is an oscillation in the up-down direction. Then, everywhere that the electric field is at its highest point, we would have a magnetic field that it's at its highest point. But they're not going to oscillate they're going to oscillate in phase, but not in line with each other. They're going to be 90 degrees or perpendicular to one another. And so the magnetic field, we're going to do in green, would be coming in and out of the page. So you could imagine that's coming out of the page, and then we're into the page. This is really hard to draw because, again, it looks like they're both in phase with each other or in line with each other. But this is more, into the page back here, coming out of the page, into the page back here, and out of the page. So you can imagine that there's this up and down movement, but there's also a side to side movement. These two different sine waves happening simultaneously and interacting and feeding off of each other. So all light, radiation, they all travel in this electromagnetic wave. And in a vacuum, electromagnetic waves all travel at the same speed. And we call it the speed of light, but it's really the speed of an electromagnetic wave, which light is one group or one type of. And the speed of light, it's 2.99. We're going to round it to 3 times 10 to the 8th meters per second. And this is the universal speed limit that comes out of Einstein's theories of relativity. And we end up with this. This is it. So all electromagnetic waves, again, whether it's radio waves, your Wi-Fi signal, all of it's going to travel at this speed in a vacuum. Now, we don't live in a vacuum. We live in an atmosphere where there is air. So it is slightly slower, but it's negligible when you compare it to the speeds we travel at. So the next thing you need to know is, the wavelength, which is from one point till its cycle has repeated, the actual distance traveled. The wavelength has a lot to do with its frequency, right, and the speed at which it travels. So we learned about this back when we were talking about simple harmonic motion and waves in general. We learned that the velocity is equal to the wavelength times the frequency. Well, this is still true for electromagnetic waves. It's true for all waves. The difference is our velocity is going to be c, the speed of light. And for the most part, this is going to allow us to calculate a ton of stuff about waves. One other thing I did want to show you in the text, just you had a kind of a basic idea of how it's related. Let's jump over here. So you can see sort of these drawing examples of in and out of the page, up and down. They're hard to draw in a two-dimensional surface, a three-dimensional image. But if we come right here, okay, we can see that electromagnetic wave spectrum is huge. And over here we have gamma rays and that dangerous radiation we think about, ultraviolet radiation, which can give us skin cancer if we stay out in the sun too much. That's why we wear a sunscreen. You've got your infrared, microwaves, things like radar, our cell phone signals right down here. These are giving us frequencies on this on this side of the table, and up here are the wavelengths. Okay, often we talk about the frequency of a wavelength, or of a wave rather, but we can see all the way down here. Okay, there's our AC current. When we want to run electrical current, we run it way down here. We've got our AM radios, we've got our TV channels, our FMs right there, our satellite TVs up here. We can see all these different sections of wavelength or frequency that we use for different things. And way over here, between 4 times 10 to the 14th hertz and 7.5 times 10 to the 14th hertz is our visible spectrum. Everything from 7.5 E-7 to 4 E-7 meters of wavelength. So when we talk about these, we'll typically talk about wavelengths. We'll say this is 750 nanometers, all the way up to 400 nanometer wavelength. Okay, so those would be our wavelengths between the two sides, or from 400 nanometers up to 750. So I want you to understand that light that we see is just a small piece of the spectrum, and it has a specific region that we're going to talk about as we go through stuff. But otherwise, that's it. That's all I got for you. You should be able to work with the C equals lambda F to solve a ton of the problems today. Good luck, and we'll see you in class.